In several of our lab projects, students have been dealing with aspects of the Linux file system. You have learned how to create and edit files, modify their access permissions, copy them, paste files together, and so on. From previous work, you are probably already fairly familiar with file systems of Windows and/or Mac OS. Every operating system has certain peculiarities to its file system, but they generally have more in common than they have different. All computer file systems use various types of storage devices: hard and floppy disks, optical drives like CD, DVD, or Blu-ray, flash drives, tape drives, and so on, as storage media for files that may contain program code or data in various formats. The files are typically organized under some sort of directory structure. If the operating system comes with a GUI, then the directories are represented as folders. This organization helps the user find information. The reason the operating system provides a file system is so the users will see a consistent logical interface to information and won't have to deal with all the varying intricacies of how to read and write different storage media, head positioning, sector size, and a ton of other things. A file, however it is actually stored on the device, is just a collection of related information, data or instructions, with a name and various other attributes. Program files can be source code, object code, libraries, executables, scripts, batch files, and so on. Data files can be raw numeric data, real or integer, data in various formats, spreadsheets, documents, presentations, characters, or text files, and so on. Most operating systems have two main classes of files, text and binary, with a number of variations on each. For example, .txt, .c, .cpp, .asm, .bat are all text files, while .exe, .xls, .pdf, and so on are all binary files. Each file has various attributes that tell us information about it. The file name is not really needed by the system. It could just use a number as an identifier, but it's there to help the human user identify it. Other information varies by the operating system and might include the file type, location, for example, its disk sector number where it starts, size, the time, date, the owner's name, protection information, and so on. Here we have a list of some of those attributes. Again, the specifics vary from one file system to another, but these types of information are pretty typical. The system needs to be able to support various kinds of operations on files. Creation requires allocating space on the storage medium and making an entry in the directory. Writing means adding new data to a file. Generally, a file pointer is used to keep track of where the data are to be written. Reading means retrieving data from a file. We can use a separate read pointer, or there can be one common file position pointer for both reading and writing. A file seek means moving the pointer without reading or writing, just to another location. Delete doesn't usually overwrite the information, just removes the file's directory entry. The data are still there and potentially recoverable until those sectors are overwritten. Some systems move deleted files to the recycle folder and only actually delete it when the user empties the recycle folder. Truncate keeps the file information or attributes but removes all the data and releases the sectors. Most systems require a file to be open before the user can read or write it, and then when you're done reading or writing it, it must be closed to commit the changes to the storage medium. Besides open and close operations, most file systems provide other functionality including moving, renaming, copying, appending, getting and/or setting attributes including permissions, and so on. The Linux cp, mv, chmod, and other related commands fall in this category. In Linux and Unix-based systems, the system calls for file functions include open, close, read, and write. The system typically needs to keep track of how many and which files are open. Often they are assigned an integer handle, It keeps a file pointer for those that are open and keeps track of the access rights and so on. Some operating systems provide the ability for a process to lock a file or sections of a file to prevent other processes from accessing that information while it is being used. There are different kinds of file locks depending on what is being done with the information in the file. There are exclusive locks for when one and only one process can access the file at a time. There are shared locks, like the reader lock in the reader's writer's problem, where multiple processes can read simultaneously, but only one can write. Not all systems provide shared locks. Locks can be either mandatory or advisory. Mandatory locks are true locks in the sense that when they are required, the operating system will prevent any other process from accessing the file. Advisory locks aren't true locks in the sense that the operating system enforces them. Instead, the application program would have to be written so it checked for the lock and respected it if some other process has exclusive access. In general, Unix and Linux do it that way, while Windows uses mandatory locks. Java supports both exclusive and shared locks. Exclusive file locks are appropriate when data are going to be modified, while shared locks are appropriate for read-only access. When requesting a lock, you specify a Boolean value, false for exclusive, true for shared. Here you see the file lock variables shared lock and exclusive lock being created. We're going to try to open file.txt in read-write mode. The first half of the file is going to be opened in read-write mode with an exclusive lock. Java will allow you to lock part of a file by giving a starting and ending location. Here, the second half of the file will only be read, so we can allow other threads to access it too. In other words, it's going to be shared. The release method is called to relinquish the lock when you're done. The last part of the code, in the finally block, makes sure that the locks are eventually released if an error occurs. Most operating systems recognize and allow users to work with a variety of file types. Some of these are for program code, source code, object code, libraries, executables, batch file scripts, and so on. Others are for data, documents, graphics, sounds, video, raw binary data, text, and so on. Many file systems support identifying the type of a file using part of its name, usually an extension, which is the last part of the file name, generally after a dot, as in .exe, .txt, and so on. These may vary from one operating system to another. Some have limits on the number of characters, and usually they are not mandatory. In other words, you can change a txt to an ext or vice versa if you really want to. So it's not a good idea to rely on the extension 100% to determine the file type. Malware may change file types to try to trick the user into executing malicious code, or an application, or the operating system, if they rely on the extensions. Some of these specific extensions are Windows or Linux or Unix specific, and others are cross-platform. Notice that Unix-like systems don't require an extension for executable files. All they need is the executable attribute. A given system may support multiple internal file structures for different purposes. At the very least, the system needs to support a binary executable file structure which contains not only the machine code, but information about how and where to load it into memory and run it. There may be other file structures defined for specific purposes. Most systems support at least text files and binary files. Some have relatively minimal structure imposed by the operating system, for example the MS-DOS FAT file system and most Unix file systems. In Unix, files are just a sequence of bytes, and the operating system itself makes no further assumptions. It's completely up to the application to define the file structure. Some other operating systems like Mac OS provide additional functionality in terms of file structure. Files can be accessed in different ways. The simplest is sequential. Information is accessed one record at a time in order. There is a read pointer and a write pointer, and we always read or write at the next location indicated by the pointers. In most cases, it is possible to rewind the pointers to their starting locations at the beginning of the file. In a few cases, it may be possible to skip forward or backward within the file by adjusting the pointers. Another common access method is direct access, where any block or record within a file can be read or written at any time. This is a much more flexible model but requires more infrastructure. Instead of just read or write at the next position, we have to specify the record to be read or written, read in or write in. N is relative to the beginning of the file, so we don't have to know exactly where the file starts and ends on the disk, which we would have to know if we used absolute disk sector numbers. Not all systems support both sequential and direct access. If the system supports direct access only, it is relatively easy to simulate the sequential access behavior. On the other hand, if a system only supports sequential access, it can be very clumsy and inefficient to try to emulate the functionality of direct access. If we have direct access functionality, we can build other specialized access types on top of it. Usually this involves building an index into the file that contains pointers to the various records or blocks of records in order to make it easier to find desired information within the file. To find something, we look it up in the index, which is much quicker versus searching through the entire file for it. When we find the proper entry in the index, we get a pointer to the actual location of the information within the data portion of the file. It's much like using the index of a book to find a particular term or topic within the book. It's much faster than reading the whole book to find the information. As in a book, where the index adds to the number of pages, the index of a file adds overhead too. In other words, extra size taken up on disk. But it can speed up access to the stored information. In organizing information, files stored on a disk, we could just have a massive collection of files with no organization. But that would make it very hard to find what we need. We need a mechanism to help us locate information so we can use it. Directories on a disk or other storage medium like a flash drive give us the ability to locate information stored in file. What is a directory? Our authors say that it's a collection of nodes containing information about all files. We can use an entire disk to implement a file system, or we can partition a disk so we can implement multiple file systems, or so we can use portions of the disk for purposes other than implementing a file system. We can use multiple disk partitions and multiple disks to implement various RAID schemes for protecting against data loss and or improving disk performance, although we won't cover the details of RAID in this particular class. A volume could be a whole disk, or partition within a disk, or it could be spread over multiple disks, for example a RAID set. Each volume has at least one directory, generally known as the root directory. A directory can be viewed as a symbol table that translates file names into their directory entries. In most cases, it is possible to create additional directories, which is something you've probably done in lab projects. Once you have a given directory in your file system, you can perform various operations within it. The search operation is there because we want to be able to find the entry, the collection of attributes corresponding to a particular file. Sometimes we may want to find all entries matching a particular pattern. This is what you did when you searched a directory using wildcard, for example ls-l lab3 asterisk. Creating a file means making a new file and adding it to the directory. Deleting a file removes it from the directory. Listing a directory shows all the files in the directory. In Linux, this uses the ls command, while in DOS, you use the dir command. You may want to be able to rename a file. Its contents may change, the way they are used may change, or we just may change our mind about the file. Finally, we want to be able to traverse the file system, access every directory and every file within every directory. This is particularly useful when we want to back up the file system, which is a really good idea since media can fail at any time, especially hard drives and flash drives. Directories can be organized in various ways, not all of which we will cover in this class. Some of the things we hope to accomplish by structuring directories within the file system are on this slide. It mainly comes down to subdividing the information into manageable pieces and grouping these subsets of information logically so we can easily find what we are looking for. For example, we might put all our applications in one directory, which we might call program files under Windows on /bin under Linux, and then subdivide that into subdirectories under that, where there'd be a different subdirectory for each particular application. The concept of having subdirectories under the root directory and then subdirectories under them and so on in a tree structure is not 100% universal in computer systems, but it's pretty common under a variety of operating systems. You have worked within a tree-type directory structure in your Linux lab projects. You had a home directory for your user files, something like /home/user, and then you created various subdirectories under that as part of the labs using the mkdir command and rmdir to remove ones that are no longer needed. Another topic you learned about in one of the lab projects was the concept of mounting a file system. Many operating systems, especially Linux, Unix, and Unix-like systems, have commands to mount and unmount file systems as well as to tell you what file systems are currently mounted. Windows normally searches for and mounts all available file systems at boot time, but newer versions allow you to manually mount file systems anywhere in the directory tree, which Unix and Linux have always done. The basic concept is that a file system must be mounted before it can be accessed. When we do mount a file system, we don't always mount it under the root directory, although obviously we need at least one file system mounted there. Most operating systems allow additional file systems to be mounted at various places. The place in the structure where we mount a file system is called the mount point, and once it is mounted, we will now find those additional directories and subdirectories and their contents beneath that mount point. Under Unix and Linux, / is the root directory. Here on the left we have an existing, already mounted directory structure. On the right we have some additional user files we wish to mount. We could do it anywhere, but in this case we might decide to mount under /users since Sue and Jane are users just like Bill and Fred. Once this is done, the files for Sue and Jane will be available under /users/Sue and /users/Jane, just like the files in /users/Bill and /users/Fred. Additional subdirectories now appear as /users/Jane/prog and /users/Jane/doc. And of course the users could now make further subdirectories and use them as long as Sue and Jane are mounted. If the file system is unmounted, then those directories and subdirectories would no longer be accessible. Most file systems allow creators of files to control how the files are used and by whom. Some of the types of accesses that might be allowed or not allowed are shown on this slide. Read access is fairly self-explanatory. Write access means the user has the ability to modify the file. Execute access allows you to run it. Of course, you'd want to make sure it's actually a program before doing so. Append access is a form of write permission. It allows you to add information at the end of the file. Delete access is also essentially a form of write permission since deleted files may have their contents written over. List access means that you're able to see that the file is there. Not having list permission would make the file invisible to a user. In Unix and Linux-based systems, as you have seen in projects, there are three types of permissions that you can have with respect to a file: read, write, and execute. There are also three classes of users who can have or be denied these permissions: the owner of the file, typically whoever created it, the group of users that the owner is a part of, and the universe, which is all other users of the system. In Unix and Linux, there is a set of 3 bits for each of the 3 user classes that determines what the permissions are. One bit is for read permission, the second is for write permission, and the third is for execute permission. If all 3 are set, binary 111 or decimal 7, then the user can do all 3 things to that file. If it's not an executable program file, then just read and write permission would be 6 or 110 binary. Read-only permission would be 4, 100 binary. Execute-only permission would be 1, 001 in binary. When you do a directory listing with the ls-l command, the file owner and group name are shown, along with all the permissions for owner, group, and universe. In lab projects, you learn how to change permissions on a file using the chmod command. This concludes the material we'll cover in Chapter 10.